Thank you. Thank you so much. This is John with Sid Barman from the Indian Institute of Science, and he's with us on the chat. So if you have typing questions, he can answer them. So very roughly speaking, this paper is about two results, two questions, which are connected. The first, a very classical question in economics, which has to do with the scope of the competitive hypothesis, or how valid it is to assume that agents take prices as given. I'll explain in a minute what this question is. And the second result is about the new algorithmic testing questions, which I'll also explain in a few minutes. So there's a more sort of an econ type of contribution, and then a more algorithmic contribution. So let me talk about price-taking behavior. You know, when you think about how the terms of exchange are determined, there are sort of two, families of models that we use. There's a game-theoretic kind of model in which two agents meet, and they, somehow bargain, somehow haggle, and they determine the terms of trade. And then we have competitive models of markets in which the agents, they take the terms of trade as given. And there's an old question, very old, formulated by Edgeworth in 1884. This is in a book titled Mathematical Physics. It's a book about economics, despite the title. And Edgeworth sort of formulates this question, and he thinks that if you take an economy and you make it bigger in a particular way, you think of a large version of this economy, then haggling will result in a competitive outcome. And the rough idea is I can convey with the following story. So imagine that Sid and I like old cameras. So I have a collection of old cameras, and Sid has a collection of old cameras, and we get together and we start thinking about, okay, so, I really like your old Canon. And Sid says, yeah, you could think of changing this by one of your Leicas. And we start talking about how we're going to exchange these cameras. Then, whether there is exchange and the terms of exchange is completely determined by, who has the most bargaining power, by how the interaction works, by which protocol we bargain. It's very hard to predict, exactly how this will turn out. But now imagine that there are many people like me and there are many people like Sid. Then, when I offer a trade to Sid, I know that if he says no, I could go and talk to someone else and make the offer to someone else who is exactly like Sid and also likes old cameras and has a similar collection. And the same thing with Sid. When he thinks about trading with me, he knows that if I reject an offer, he can go and make the same offer to someone who is exactly like me. So this is Edgeworth's idea. If you take a replica of the economy, you consider economies in which each agent is no longer very special because there are many people like them, then what you will get in the limit will be determinate and will actually be a competitive outcome. And the possibility that this is true is called the Edgeworth Conjecture. So the Edgeworth Conjecture has received a lot of attention in economics over the years. The very first, very famous results about this are due to Barman and to the Debreu-Scarf, who prove under different models of what a large economy is, that in a large economy, when no agent is no longer unique, bargaining power dissipates, and the outcome of bargaining approximate the Walrasian equilibrium. So think of, when I bargain with Sid, I have certain monopoly power as a supplier and monopsony power as a consumer. Well, when there are more people like me, this monopoly and monopsony power starts to go away. And then in the limit, we get competitive outcomes. So we are going to provide a result along those lines, but where the bargaining is limited. So in particular, we're going to look at the core with coalitions of limited size. So if you don't know what the core is, just bear with me for a couple of slides. I will give you the definition. But roughly speaking, coalitions of size order of h squared times L over epsilon squared are going to be sufficient, where h is the heterogeneity of the economy. I'll show you soon what that means. L is the number of goods, and epsilon is the approximation factor. And we're going to do all this in a very classical Debreu-Scarf replica model. The next result has to do with a new algorithmic question, and the question can be quickly formulated like this. Given an economy and an allocation X, are there prices P such that the allocation with those prices constitute a Walrasian equilibrium? So you may be familiar with the second welfare theorem. In the second welfare theorem, we have an economy under certain assumptions. Any allocation which is Pareto optimal can be decentralized as a Walrasian equilibrium using prices, but not just prices. You need to also make some transfers and some subsidies. And the reason why those can be problematic is that because if you want to control the welfare of the agents in this economy, we want to see that there's no envy, or we want to obtain want to control what the ultimate income of the agents are, then the taxes and the subsidy are going to be subservient to the allocation that we want to allocate. So here, we don't use transfers, we don't use subsidies, and we want to know when there are prices such that the X is exactly a Walrasian equilibrium. Well, actually, approximate Walrasian equilibrium, but one without transfers and subsidies. And in the paper, we provide a polynomial time algorithm that, when we make the right assumptions on the economy, we're going to decide this question. Now, this is, an interesting question, we think, in itself, but you may be particularly interested in the contrast with the existing results on hardness of Walrasian equilibrium. So, by now it's a collection of results that show that finding a Walrasian equilibrium is hard, even under very lenient assumptions on the economy. Even you think extremely well-behaved economists, it's hard to find a Walrasian equilibrium. So, in contrast with these results, we prove that finding prices is easy. If you have the allocation, deciding whether there are prices and finding those prices when they exist is easy. And this is true also under assumptions on the economy under which we know that it's hard to find a Walrasian equilibrium. So specifically with Leontief utilities or piecewise linear concave utilities, in which it is known that it is hard to find a Walrasian equilibrium, we prove it's easy to find prices once the allocation is known. So in that sense, this contributes to the literature on the complexity of Walrasian equilibrium. So that introduction, let me go to the model. The model is a very standard textbook model of a Walrasian economy. So we're working with an exchange economy, which is described by a set of consumers and a collection of goods. So there are H consumers, and there are L goods. Each consumer is described by a utility function UI and by an endowment omega I. So the consumer is born with a utility function, and is that 10, Irene? I don't see the whole hand. Okay, 10. Okay, good, got it. Okay, so so each consumer is born with a utility function and an endowment. Then they go to the marketplace and they trade. An exchange economy is then a collection of consumers, each with a utility function and their endowment vector. I'm going to make some assumptions on utility functions. So first of all, the UIs are continuous and monotone increasing. You know what that means. We are going to assume, mainly for simplification, that utilities are continuously differentiable. And we are going to make some assumptions to control the curvature of the utility function. So for expositional reasons, we focus on alpha strongly concave utilities. So remember, if a function is concave, then when you use the gradient to estimate the function, you will overestimate it. So if I have the function, the value of the function at x, and then use the gradient to estimate the value at y, then I will overestimate it. Well, alpha strongly concave tells me, refines the bound by this parameter alpha. And this is one way of controlling the curvature of the utility. There are other ways of doing it. But mainly for presentation, we focus on this one. Okay, and location in an economy is a way of allocating the sum of the endowments. So if you add up all the vectors of endowment, this is called the aggregate endowment. You just divide that up among all the consumers. That's an allocation. We normalize utilities so they lie between 0 and 1. This is a standard thing. The set of all allocations is compact, so you can just and the utilities only have normative, only have ordinal meaning, so I can normalize them. So this is an innocent step. And now I'm going to tell you what the core is. So this is a really important concept. An allocation is, I already told you what it is. It's a way of dividing up the aggregate endowment. Any non-empty subset of agents or consumers is a coalition, and a coalition can take their endowment. So if they add up the endowments of the members of the coalition, they can divide up among themselves, and that's called an S allocation. Now, a coalition blocks an allocation if there's a way that they can reallocate the endowment that they have that makes them all strictly better off. So a coalition X blocks the allocation X bar if there's an S allocation YI, which is strictly better for all the members of S. And the core of E is the set of all allocations that are not blocked by any coalitions. So when I said that we have a game-theoretic formulation of bargaining, this is what I meant. So in this, you can formulate an exchange economy as an NTU game, and then this is a standard solution concept from cooperative game theory. Very good. So in this paper, we are going to be working with something we call the kappa core. So the kappa core is the set of allocations that are not blocked by any coalition of cardinality at most kappa. So note, the core requires me to check that no coalition wants to block. The kappa core only requires me to check that small coalitions want to block, and that a small number of coalitions want to core, because there aren't that many coalitions of size kappa. So the advantage of the kappa core is that it doesn't require assuming that agents can organize in extremely large groups. So it only requires that agents organize in small groups. And from the viewpoint of checking whether something is in the core, it doesn't require me to check for blocks by a large number of coalitions. Very good. That's the core. The next notion is something you're familiar with, is the notion of Walrasian equilibrium. So a Walrasian equilibrium is a pair, a P and an X, where P is a price vector. Every agent exhausts their income that they obtain from selling their endowment at the prices when they buy X bar I, and they are maximizing utility, meaning that if something is strictly better for them, they can't afford it. And finally, if you add up all the X's, you get the same as by adding up all the endowments. So this is just market clearing. So this means supply equals demand. And an epsilon Walrasian equilibrium is a pair of P and an X in which each agent is within epsilon of spending all their income, and for any bundle that makes them strictly better off, they are within epsilon of spending more than what they have. Okay. Now you might think this is not, and you have market clearing. Okay. So you might think this is not the notion of approximate Walrasian equilibrium that you're used to, but it turns out you can move in between this and the other notions in an easy way. So you can find that in the paper. Next, I need to quickly tell you what a replica of an economy is. And what a replica of an economy is what you think it is. So take an economy, the nth replica of the economy E, which we denote by E super M, is just a copy n times of all the consumers. Okay, so you're going to have n times H consumers. Okay, and each consumer is going to be identical to their prototype. So copy I of consumer T has the same utility and the same endowment as the prototype T. An allocation has the equal treatment property if all the consumers who have the same type are allocated identical bundles. And then we have a lemma, which is called the equal treatment property, which says that if utility functions are strictly monotonic, continuous, and strictly concave, then every kappa core allocation has the equal treatment property. Now, the very famous theorem from 1963 is that if an allocation is in the core of every replica of an economy, then there are prices such that it is a Walrasian equilibrium. And this is a proof of the Edgeworth conjecture. So notice that because of the equal treatment property, even though I'm looking at the replicas of the economy, I can represent the allocations as allocations of the original prototype economy. And then it makes sense to say that X is in the core of every replica of the economy. So our first result says, for any epsilon, if UI is monotonic, C1 and alpha strongly concave, and if X bar is in the kappa core of EM, where kappa is lower bounded by this magnitude, which has these guarantees that I mentioned at the introduction, of dependence on H epsilon L, and lambda is a Lipschitz constant on the utility, then there are prices such that this constitute a Walrasian equilibrium. So this is what I meant by the result that only requires that that the allocation is in the core for small coalitions. Okay, very good. Now I will give you the testing result. So assume I have black box access to utilities and their gradients, and let epsilon be an exchange economy. Then if every utility function is monotonic, C1 and strongly concave, there's a polynomial time algorithm that given an allocation Y bar in E decides whether Y bar is an epsilon Walrasian allocation. Okay, so this is the algorithmic result that I promised. The connection between these two, you have to find in the paper. Basically, there exists a way of representing epsilon Walrasian allocation that lends itself to proving versions of the Edgeworth conjecture, and at the same time, to think about this testing question. And yeah, let me skip this. A key idea in the proof is the use of the Approximate Caratheodory theorem, which Sid wrote a paper on in 2015. It says that if you have X in the convex hull of a finite set of points, then you can represent it as a convex combination of at most K, P, gamma squared over epsilon vectors. So notice this is dimension independent formulation, where P is the norm we use, gamma is the largest size of these vectors, and then epsilon is the approximation guarantee. So let me very quickly just flash the literature for you. There are these, like I said, core convergence is a very, very studied problem in economics. Surprisingly, no one has, obtained a type of result we have. The closest thing is a paper due to Mascolelli in 1979. This started in the 1880s, so there's a very long literature on these things. There's a survey, I recommend this survey by Anderson in 1992. It's a book by Hildebrand, beautiful book, 1974, if you're curious about these things. In the EC audience, I'm sure is familiar with this literature on testing on the complexity of equilibrium. There's a book by Chakiadis, Elkin, and Woolrich on computational equations in cooperative game theory, and this sort of fits in with that. And I think my time is up. So thank you.